divided into several major areas such as machining, casting, forming, molding, joining, and additive manufacturing. Machining is a subtractive process that removes material to create a desired shape, such as turning, milling, grinding, and drilling. It's about 15% of engineering component can be produced by machining process. The key element of the any turning process are cutting tools, workpiece material, and cutting fluid. D2 steel is air hardening, air carbon, high chromium tool steel. It has high wear resistance, strength, and hardness, good toughness, mild corrosion resistance. These properties, of course, made D2 is a very attractive material for production of press tools, cutting tools, plastic molding, and pressure die casting dies. However, D2 is not is one of the difficult to cut materials, and machining D2 is still challenging comparing to the low alloy steel. Unlike conventional tool, which is very common in single tool based machining operation, wiper tool, which is in the lower pictures, wiper tool attracted close attention as a good alternative to conventional cutting tools due to its unique nose geometry. As we see here, the conventional has a clear roundness, but the wiper geometry is different from standard tools. Of course, by using wiper tools can reduce machining time, better chip breaking, improve service finish at high feed rates, eliminate the finishing steps by roughing and finishing together. Based on the current literatures, a limited research were conducted on machining D2 steel using different tool geometry, such as wiper tool. However, only few studies were recorded a notable improvement in service quality when machining D2 alloy steel using wiper tool, while others are not. Therefore, this research will fill the gap by answering on the following questions. Does the cutting performance of both tools are similar in terms of service quality when wet turning of D2 tool steel? Does tool geometry outperform other operating parameters in terms of service quality during wet turning of D2 tool steel? Process optimization utilizing Taguchi methodology is the principal aim of the study. To serve this aim, the following specific objective should be accomplished. To investigate the influence of tool geometry and the other operating parameter on service quality, to identify the optimal cutting condition and the most significant process factors affecting surface quality, and finally to investigate the interaction effects of a process factor for surface quality. Slide shows all the design of experiments, methodology and design experiments with orthogonal array, 16 tests, and operating parameters or process factors and level are shown as in the table: feed rates, cutting speed, depth of cut, and tool type. All of them are with two levels: feed rate 0.15, 0.25, cutting speed, rotational cutting speed 1000 and 1150, depth of cut 0.5 and 1 millimeter, tool geometry or tool type is wiper and conventional one. Experimental setup and material tools, we use the CNC machine tool for the experimentation. Cutting tool is CVD, chemical vapor deposition coated carbide tool for both wiper and conventional tips. workpiece dimension, it was 20 millimeter in diameter and 60 millimeter in length. The measurement tool, we used digital surface tester and optical microscope. And we used Minitab software for data analysis. This is the experiment runs, which is 16 tests, and measured value of surface roughness, average surface roughness. This is the average surface roughness of all tests. And here the analysis of mean diagram clearly shows that the optimal cutting condition can be obtained at 1150, which is the smaller is the better surface roughness. The smaller is the better. Smaller surface roughness, that means better surface finish. So minimum is the best. So 1150 cutting speed, 0.15 feed rate, 0.5 depth of cut with wiper cutting tools. This is the recorded optimal cutting condition. This is the analysis of variance, which is called ANOVA. Analysis of variance ANOVA show us that the tool geometry showed the highest influence on surface quality, surface roughness, with percentage contribution ratio 32.85. That means this is the significant one. B should be less than 0.015. So all factors here are more than 0.015, but if we see here, tool type is 0.016, which is reject the hypothesis, null hypothesis. That means it is significant. Also, feed rates and tool type show the highest significant interaction effect for surface roughness with the percentage contribution ratio 26.82. Interaction plot diagrams shows that there is a mutual interaction between feed rates and tool geometry or tool type. This one, that's clearly there's an interaction between two factors. The other is it's a slight interactions, so it's trivial. But this one, it's a mutual interaction. This confirms the ANOVA results that the interaction between feed rates and tool geometry is significant with the percentage concentration ratio, contribution ratio 26.82, as we mentioned previously. This indicates that the relationship between tool geometry and surface roughness depends upon the feed rates level. The contour plots shows the relationship between the operating parameters, cutting speed, the feed rate, the depth of cut, and tool type or tool geometry, and their influence on surface roughness. Dark blue zone show lower surface roughness values, while dark green display the higher surface roughness value, which is not good. Light blue and green show moderate value of surface roughness in briefly. Surface topography results shows that the surface generated with the wiper tool is smoother than the surface with conventional tool with finer feed marks. This is the images of topography surface by conventional standard tool. As we see here, there is a wider feed marks, which is not preferable in machining. Compared with the wiper tool, we see here finer feed marks, which is good, which is better compared with the conventional one. Validation. To validate the results, 3 runs were performed at the same optimal cutting condition as the confirmation tests. Only a small error, 6.4%, was reported, which is within acceptable acceptable range. As we see here, this is the predicted surface roughness by the software, by Minitab, and this is the real measured surface roughness, and this is the difference. It's very, very, very small. This is in micrometer. Remember, this is in micrometer, which is very, very small, and the error is 6.4. So that means a good confirmation between the predicted surface roughness by software and the real experimentation. Conclusion. Optimal cutting condition can be obtained at 1,150 rotational cutting speed, 0.15 feed rate and 0.15 feed rate and 0.5 depth of cut with wiper tool type. The wiper tool or tool geometry significantly enhances the surface quality when turning D2 tool steel, while the cutting tool geometry being the most impactful factor with the percentage contribution ratio 32.85. This is the key finding of the work, and this is the answer of the questions as mentioned previously in the second or third slide. This is the all answers of the questions. So that means wiper tools significantly enhance the surface quality, and the cutting tool geometry being the most impactful factor compared with the other parameters like cutting speed, feed rate, and depth of cut. Notable interaction was observed between feed rate and tool type with the percentage contribution ratio 26.82. This indicates that the relationship between tool type and surface roughness depends upon the value and level of feed rate used. And finally, the study validates the efficiency of Taguchi method for process optimization in machining operation. The future work will be in investigation the effects of tool geometry and operating parameters on tool wear and chip morphology based on response surface methodology RSM for turning D2 alloy steel. Hopefully will be this is within next month. And finally, knowledge is given to all supporting lab staff and collaborator at Libyan Authority for Scientific Research. And thank you for your listening. Any questions?
Thank you very much. Any questions? I have a question, Dr. Better cutting machines.
Sorry. Could you please repeat?
Yes. Do you think that a virtual environment with for all this machinery would help you experiment, make experiments, and build better machines for these cutting technologies?
That's a good question. Yeah, of course, virtual machining it's now booming, of course. But we should validate this results with some experimentation. Of course.
Yes, of course.
Let's stay it's virtual because here we are not gambling because yes, all this experimentation is beneficial for the manufacturer. So manufacturers not gambling. They need a real look. This is like for mass production. So the operator they need the optimal cutting condition to produce thousands or hundreds of spare parts. So that's need they need a real numbers of optimal cutting condition. But that means, of course, the simulation and the virtual. That's good. At least to minimize the resources and the cost of the implementation.
Yes, mainly for educational purpose before they go to the real stuff. Okay, that's what I mean.
I'm fully agree with you. Yes. Thank you.
Thank you. Any other questions or comments? No. Okay, so thank you all for all your great presentations, your excellent contributions. And this session, I think, gave us a wide range of innovative data-driven approaches that will be helpful for the future of smart manufacturing and intelligent systems. It's been a pleasure to chair this session. Thank you very much. Enjoy the rest of the conference, and maybe we can meet in the next year's ISM conference. Okay, thank you very much.
Thank you, Doctor. Thank you.
Thank you all.
Thank
you
you
all.
Have a good day.
Bye.
Thank you. Have a good day. Bye.
Have a good afternoon. Bye.
Thank you.